Okay, so look at a few things that you need to know about NMR, a few NMR basics. Okay, so one thing you need to know about NMR is that your sample is being put in a magnetic field. So there's a big electromagnet, huge electromagnet around your sample, and then it is bombarded with radio waves, low frequency or low energy radio waves, and some of those radio waves will be absorbed by your sample as it realigns its nucleus to match what's going on with the magnetic field. So the energy that is absorbed by the sample is in the radio waves part of the electromagnetic spectrum. Okay, it's important you know that. So what does that relate to then? Well, depending on your environment, you'll get different peaks. Okay, so one thing to realise straight away is that there's a completely different set of graphs, spectrums for carbon NMR, carbon-13 NMR, which is this one, and hydrogen-1 NMR. Okay, completely different scale. If you've got the hydrogen-1 NMR, it tends to go from 0 to 12, while this one for carbon-13 goes from 0 to 220. So completely different scale, but they're both measured in parts per million. So basically what happens is your sample realigns itself with the magnetic field, going from low energy to high energy state, and when it does that, it absorbs some radio waves to be able to jump from one energy level to another. Okay. Now you don't need to know much about that, but what you've got to realise is when those radio waves are absorbed, what frequency of radio waves it absorbs corresponds to where the parts per million is, and different hydrogens and carbon-13s in different environments will absorb at different frequencies and hence have different parts per million. So if we look at the hydrogen one first, you can see each one of these hydrogens is in different environments. This one's a hydrogen on a carbon and a double bond. Here's a hydrogen of a carboxylic acid. Okay, if we go over here, this is one you probably see most commonly, is a hydrogen just bonded to a normal R group. So that would be like your normal alkane, that kind of thing, normal alkyl group. We've got here, this is one you see quite a lot, is a hydrogen bonded to a benzene ring. So if you get a peak between 6, 7, 8, it quite often will be a hydrogen bonded to a benzene ring. Now you notice quite a lot of overlaps here as well. So the parts per million, it isn't something we can use to definitely say this is this. It doesn't work quite like that, okay? But it gives you an indicator, gives you an idea. So quite often you need to know more about a molecule rather than just the NMR. It'll be hard to identify a molecule simply from NMR. You need more information. And that's why it's quite often combined with other techniques like mass spec and IR. Okay, these ones here, the asterisks, these are hydrogens bonded either directly to oxygens or to nitrogens, and one over here as well, and they tend to be broad. So a lot of these peaks are very sharp, almost like needle-like. These ones are a little bit more rounded, so sometimes that can be a clue when you're looking. But if you look, they have huge ranges where they could be. So where it is on here, the parts per million, doesn't tell you a huge amount. Okay, it's just a rough guide. Carbon NMR is a little more located along the spectrum, different scale again. Okay, all these ones are needle-like. So it just shows you the carbon-13, what environment it's in, and here's in different environments. Okay, so all these parts per million are in reference to TMS, tetramethylsilane. So every time you do an NMR, you put in a small amount of TMS, okay? And that always gives you a reference at 0 parts per million. Now sometimes they'll draw that on, they'll have a peak at 0 parts per million, which if you do, it's a reference. Sometimes they just remove it because you know it's going to be there. But everything is aligned to this. So here are TMS. Let's take that actually a bit of silicon. Okay, and you've got silicon bonded to 4 CH3s. All these CH3s in the same environment, so you've got 12 hydrogens in the same environment, and that always gives a clear peak at 0 parts per million, and everything is aligned according to that. So it basically shows us where 0 parts per million is. Something else that you need to know about NMR, in terms of conducting an NMR, is that your sample has to be in solution. So we need a solvent that will dissolve it, okay? So something that's good at dissolving lots of normally organic molecules, but also something that won't have a peak itself, otherwise it could interact with our sample and make our spectrum very confusing. So we often use deuterated solvents, And that's where the hydrogen, so this might have been an H originally, a hydrogen has been replaced by deuterium. Deuterium is basically H2, an isotope of hydrogen, but because it's got an even number of nucleons, it doesn't show up on the NMR. So this is really good at dissolving things, CdCl3, but it doesn't show up a peak on the hydrogen NMR itself. Okay, so that is a very common solvent. But it doesn't have to be CdCl3, but all the solvents that we use in NMR will be deuterated, so they don't have any hydrogens.